This is the notes for 1.4, recognizing linear relationships. So our vocabulary word today, in order to be a linear relationship, there must be a constant rate of change between the two variables. So for each independent, I'm putting in x, there's a constant change in my dependent, what I get out, y. Okay, so in this picture over here I made to myself, a linear straight line has a constant rate. So whether I go up and over a different amount every time, as long as it simplifies to the same fraction, that is linear. Okay, so going up 4 over 2 is the same as going up 2 over 1. Whichever order pairs I choose, I should be able to simplify and get a constant rate. So in our example from yesterday, Gilberto in his table, remember we were adding $2 for every meter he walked. $2 for every meter he walked. That was a consistent rate. Okay. A nonlinear function would be something where it curves, okay, so something funky like that, or it can also be straight but not constant, okay? So this one started out linear, but as soon as it changes, my rate is not a consistent $2 per meter. This is no longer a linear function. We can't write something like this. Or if it happens decrease, or it gets even steeper, okay? Even though it's a straight line, I cannot write one function without covering up part of it. Okay, so just this is linear, just that would be linear, right? Just that little part right there is linear. But as a whole, this is not a linear function. Okay. The other thing to keep in mind, in order to be proportional, it must start at 0. Okay, so as soon as I add something, so like let's say Elena, she added $5, I cannot add something and write a proportion still for it. Okay, so for Elena, she was getting 50 cents per mile, 50 cents per mile, 50 cents per mile. That is a unit rate. We could write that as proportion, but I can't include the +5 in my proportion. It throws it off, okay? So in order to be a proportional relationship, it has to start at 0, 0. I want to be able to write it as $2 over 1 meter and not have anything extra there to put with it. So in order to be a proportion, I have to start at 0, 0. I can't add anything like Leanne or Elena did. All right, so let's try an example here together. So Susan bought some new workout equipment. It's expected to last 8 years and therefore depreciates an average of $200 per year. So if she paid $1,600 for the machine, sketch a table and a graph of this relationship. So we said she paid $1,600 originally, and then it's depreciating. That means she's losing $200 every year. So after 1 year, she's at $1,400. After 2 years, she's at $1,200. After 3 years, if she wanted to sell it, it would only be worth $1,000. As she uses her elliptical, things start to break down, so she loses what she could sell it for the following year. Right? She keeps using it another year, now she can only sell it for $800. Okay, they're making the assumption that after 8 years, 8 times 200 is 1,600. There would be nothing left. So the machine's probably too broken, she wouldn't be able to sell it for anything. So if I was to write an equation, that would be my cost is what I'm getting out. So that's my dependent variable. My cost C is what I put in the number of years. So in this case, she's losing $200 times the number of years. Remember, I don't need my multiplication dot. A number and a letter side by side already means to multiply. So we can just say negative 200y. That means she's going down $200 for every year. Okay. In our graph, we're going to see that as a straight line going down, right? We know we have a slope. So in our table, every time she's losing $200 for every 1 year she goes. She loses here $400 after going 2 years. Either way, she's losing $200 for every year. Or in our equation, right, there's our slope. She's now going downhill $200 for every year. So I'm going to label mine by ones. I'm putting in her number of years, and what I get out is the value. Keep in mind, she needs to go all the way up to 1,600, so I'm going to go ahead and just count by 200s. If your scale needs to get up to something bigger than 1,000, you're probably going to count by hundreds. If it's like 2,000, you're going to count by 200s. Okay. In our case, since she was going down $200 per year, I went ahead and just counted by $200 every year. If you're counting by something different, then your graph will look slightly different if you come to check it against your teacher. So at 0 years, it's worth $1,600. After 1 year, it's worth $1,400. After 2 years, it's worth $1,200. After 3 years, it's only worth $1,000. 4 years, $800. By the time she gets down here, after 8 years, it should be worth nothing. So this is a straight line where my slope, every time she's going down $200 for every 1. She goes down $200 after going 1. Okay, so remember that's my constant rate of change. It's $200 for every year. $200 for every year. Okay. The distinction though is that she started at 1,600. So in this equation, if I was just going to put in a 1, negative 200 times 1 is negative 200. But we said she was supposed to get up here at 1,400. Well, that implies that we started at something bigger than 0. Okay, so if I test this out, 0 times negative 200 is still just 0, then I would get out my 1,200. After 1 year, then I get to do negative 200, and I would get to 14. Or let's say if I put in 4. 4 times negative 200 is negative 800, so negative 800 plus 1,600 is 800. Okay, so you see that? So my rate is going down 200 for every 1. Just like in our table, we see it's consistently down 200 for every year. That repeat addition, though, turns to multiplication in my equation. The new thing we're adding today, though, is that if she wants to start at 1,600, she needs to add this. Okay, so that's the difference. Yes, my graph is linear, okay, but no, it's not proportional because it starts at 1,600, right? I couldn't write a proportion that did negative 200 for every 1 year, because if I was going to find X number of years, let's just say 4, negative 200 times 4 should be negative 800. There's no way for me to include in here the 1,600. Okay, so that's why we're going to say no, it's not proportional, but it is still linear. I have a constant rate where she's losing $200 for every year. Okay, even though it starts as something different, we can show that in an equation by adding. We just unfortunately cannot show it in a proportion like this. Okay, so in your example today, in the book investigation, keep in mind it's depreciating. She's spending money every week, so your graph should be going downhill when she's losing, when she's subtracting every week, but it says she'll be a constant rate. So whatever she starts with, as she spends money out of her bank account, it's going to be a straight line that goes down.